We're on lecture number 3 for CIVE 360, and last time we introduced one of our more complicated problems to date, and that answers the question, what happens if we take a rectangular section, I'm going to look at a side view, and rather than cutting it like this, we slice it at an angle theta. So that angle is going to be from the vertical, and that's going to be important to remember. So we call this stress on an inclined plane. And this happens a lot. You can see this actually in wood construction. There are things called finger joints where they have things that look like this and they're joined together. And they'll be on weld lines and connections and so on. So it is not an abstraction. This is a very real phenomenon. It happens all the time. And what happens is it generates both a normal and a shear stress on that cut plane. I'll draw that by going like this. There's a sigma, and then there's also going to be a tau. And our job then is to find out what that's supposed to be. So what we found last time was these two formulas. We have that sigma is equal to P over 2a times 1 plus the cosine of 2 theta. And then we found that tau was equal to P over 2a times the sine of 2 theta. Now, I boxed those up mainly because they are important. They're very useful to us, and we're going to be able to use these a number of times, but you don't have to commit those to memory. So I will say star. In other words, they're important, but you don't have to memorize. So no mem. So they are important, but again, of all the things that you have to commit to memory in your brains, I wouldn't put this as a top priority. If you want to, that would be great. But what we do want to do is pull out some critical values that we have. And so one thing that we're always interested in is to ask, what are the max and min? So what are the maximum normal stress and Tau max? And the thetas at which they occur. So let's take a look at those. If we look at the value of sigma, for example, then we know that the cosine of anything, the absolute highest value that it can reach is 1, and the smallest value that it can reach is -1. So the peak value of that is of the cosine of anything is going to be the value of 1. So we know that the sigma max that we would get would be P over 2a times 1 plus 1. And so that's going to have 2, that's going to cancel, and that's going to be equal to P over a, which not coincidentally we've seen before. So we have to ask then, when is the cosine of 2 theta equal to 1? And of course, that's going to be when theta is 0. It's the cosine of 0 that is going to be equal to 1. And so that's back to our original problem where if I take a side view of it, we slice it like this. That means that our cut angle, theta, is going to be equal to 0, and that means it's perpendicular to the applied load P. And remember what that did for us. That meant that all of that action was resisted by a normal force, and the cut area is actually equal to the area of the cross-section. So we can find then that at theta is equal to 0, we have sigma max, which is equal to P over A. Now that I do want you to commit to memory, and actually let's go one step further. What's the value of tau on that plane? So we go back up here and we realize that when theta is equal to 0, the sine of 0 is 0, so there's no shear stress. And that makes total sense. So at theta is equal to 0, the value of sigma hits its max at P over A, and we also find that tau is going to be equal to 0. Now that I do want you to memorize. That's important. So the largest stress that you can get in an axially loaded bar is going to be P over A. And so that's nice for us because it tells us what a critical value is going to be. So things kind of condense to the simplest possible state in that case. All right, well, what about Tau max? So if we look back at Tau max, in fact, let's rewrite it. So Tau max, question mark. Well, remember that tau is equal to P over 2a times the sine of 2 theta, all by itself. Once again, we remember that the peak value that the sine of anything can take is 1. That's the absolute highest. And so that means that tau max is going to be p over 2a just times 1. So we can write then that tau max is going to be equal to p over 2a. Now notice how important that is. It's half the value of sigma max. So it is 1/2 of sigma max. We're going to see that play out over and over again during the course of this class. And when does that happen? When is the sine of anything equal to 1? Well, that's when 2 theta would be equal to 90 degrees. So the sine of 90 is 1. That must mean that theta is at 45 degrees. So tau max occurs at a theta of 45 degrees. Now, what happens to the sigma on that plane? So in other words, if I take a cut and go at 45 degrees, like so, then we know we're going to hit the maximum value of shear. But what is sigma? Let me rewrite it. Sigma is p over 2a times 1 plus the cosine of 2 theta. Well, when theta is equal to 45, we get the cosine of 90. That's 0. So we simply have that one is going to be gone at theta is equal to 45. And we find that sigma is p over 2a. So the sigma on the plane where tau is a max is p over 2a. So that's kind of cool. I'm going to box this whole thing up, even though you really have to only pull out a few things. So that means then that both sigma is p over 2a. So this is my p. And I also have a shear stress that's p over 2a. So that's kind of cool. We have a plane on which the normal and the shear stresses are exactly the same, and that's going to be at 45 degrees. So again, I'm going to put off to the side. We will see this again. This is kind of the first time that we'll see this phenomenon of what happens on this particular cut plane. Now we might want to ask, we know where tau is a min. That's at theta is equal to 0, it's equal to 0, the value of the shear stress. But what about sigma? Is there any way to get that value of sigma equal to 0? So on that we would say sigma, in fact I'll say can sigma equal to 0. Sort of. Now remember we did the lap joint problem, and that was the problem where we had the two boards like this side by side, and we glued boards like this and then like this. And all we got was a tau sigma was equal to 0. The inclined plane, unfortunately, it kind of breaks down because what we would require would be that 1 plus the cosine of 2 theta, we would need that to be equal to 0. That means that this would be equal to -1. And the cosine of 2 theta, that means that theta would be, since I want the cosine of 180 degrees, that would be -1. That would be the theta would be equal to 90 degrees. Well, can we realize that? That means that if I took it, my cut plane, again, it's from the vertical, it would have to be at 90 degrees. That's along here. So what would happen is we would have a cut that basically bordered this wall. So we can never quite get there for the analysis that we did. We have to have theta be less than, not equal to 90 degrees. So this formula breaks down. So we can only say then that for this particular model, we can only approach a 90 degree cut. We cannot hit it. And again, if we do that, we realize that we've run out of our problem. We've run out of our domain. But I could take it and go really, so let me approach it. We could make a really long cut like this. So that would be something like 89 degrees or something like that. So that we could have, but we cannot quite hit that one because then we really don't have any more section left. So there is a little bit of a limitation inside of our analysis. So to close out, and we'll do a numerical example on this, pardon me, but we can close this out by kind of summarizing things. Here's what I want you to commit to memory. In that if we have an axially loaded bar, so that's what we would call an axially loaded bar with a cross-sectional area of A and P and theta. So A is a cross-sectional area, P is the applied axial load. And when I say axial, that means it goes along the direction of the bar. So if it's a 2x4, it's going in the long direction, a piece of rebar, a pencil, and so on. So it's only loaded by its axis, and we have cross-sectional area, the applied load, and the cut angle theta. Then the things that I want you to remember are that sigma max is equal to P over A at the theta is equal to 0 degrees, and that tau max is equal to half that value, P over 2A. That's going to be at theta is equal to 45 degrees. And on that plane, on this plane, we have that sigma, I'm not going to write max, it is the normal stress on the plane where tau is at a maximum, is also going to be equal to P over 2A. I'll say at theta is equal to 45 degrees. So I'm going to box that up, and once again, that is the kind of the end point that we have of this particular analysis. Now, I will assign a homework problem or two, and it's okay to use those formulas that we have, but here's what you need to watch out for. A lot of times what they'll do is they'll do something like this, and then they will give the angle here. They'll say this is something like 60 degrees. Find the stresses on that particular plane. So warning, make sure you convert the angle. Convert to the distance or the angle from the perpendicular line. So if this is the load, this is the perpendicular line, and that's our theta. So it's this. So in this case, the theta would be equal to 30 degrees, not the 60. So just be aware of that as you take a look at some of the homework. But we're going to do an example problem next. But for right now, that is done for part A.